Alright, in addition to looking at how to calculate the rate of a reaction by measuring either product increase or reactant decrease, we also would like to use the kinetic information to determine what's called a rate law. A rate law is an expression that describes how concentration changes in our reaction will affect the overall rate. And we can use the kinetic data to determine the rate law. Generic rate law is set up in this way. The rate of the overall reaction is equal to a rate constant K, and we will talk about that later, times A, the initial concentration of reactant A, raised to a power of X, times initial concentration of reactant B, raised to a power of Y. X and Y are reaction orders. They are exponents that represent how much concentration changes affect the rate. The rate constant K and the reaction orders for each reactant must be determined experimentally using the kinetic data. They do not correlate with coefficients from the reaction. There are three types of reaction orders that we're going to worry about for this class: zero order, first order, and second order. And the reaction orders are the exponents to which your concentrations would be raised. So if a reactant is zero order, we would say that A, reactant A, is raised to a zero. And of course, any number raised to an exponent of zero is 1. So this indicates that the rate is not dependent upon the concentration of A. In this case, the rate would be equal to the rate constant K. So if a reactant is zero order, the concentration change of that reactant does not affect the rate in any way. First order reactions have an exponent of 1. Any number raised to the first power is just the number itself. So we would say the rate is equal to K times the concentration of A. This would be a 1-to-1 relationship. As A changes, the rate changes by the same amount. So if A doubles, the rate doubles. If A triples, the rate triples. If A is cut in half, the rate is cut in half. And then second order. This has an exponent of 2, so we have a squaring effect. So if the concentration of A doubles, the rate quadruples. If the concentration of A triples, the rate increases by a factor of 9. If we look at how these reaction orders affect the rate information, we can see similar graphs to what we saw previously. In the left graph, we have concentration of reactant A versus time. So this is the same kind of graph we saw earlier in the previous video. Now the reaction order will make the graph look different. So if I have a zero order reactant, remember, zero order reactants, concentration does not affect the rate, so my rate stays constant and I have a straight line. So remember, for these graphs, the rate is the slope. So if I have a zero order reactant, the slope stays constant and my line is straight. If I have a first order reactant, shown in the green line, as concentration changes, the rate changes. So I see a curved line. So in this case, as my concentration of A decreases, my rate starts to slow down. Okay, so remember that first order effect. As my A is going down, my rate is going down by the same amount. So I see that my rate decreases as my concentration decreases. The red line shows a second order reaction. For second order, we have an exponential effect or squaring effect. So as A decreases, our rate is decreasing by an even greater amount. So I can see a more defined curve. My rate is slowing down faster with second order. The graph on the right shows rate on our y-axis versus concentration of A, which is a reactant, on our x-axis. So we can see a different phenomenon, but even easier to determine the reaction orders based on this graph. So for zero order reactions, concentration does not affect rate. So even though A changes, rate stays constant. So I have a horizontal flat line with a slope of 0. Alright? In this graph on the right, rate is not my slope. Remember, rate is on the y-axis. So this just shows that rate is constant. The green line is our first order reactant. So as A increases, rate is going to increase by the same amount. So this is that 1-to-1 relationship. And so we see a slope of essentially 1 on our green line. For second order reaction, we have a curved line indicating the exponential effect. As A increases, the rate increases by an even greater amount, so the rate is squared. Using either of these types of graphs, we can tell a difference between reaction orders for each reactant. Reactant orders are very useful because they tell us how the concentration changes will affect the rate for each individual reactant. So if we look at the first example here, NO plus O3 produces NO2 and O2. We want reactant orders for each reactant. We don't have reactant orders for products because products do not determine the rate of a reaction. Only the reactants do. So our rate law only contains our reactant information. Rate is equal to our rate constant K times our NO raised to the first power. If we don't see an exponent marked, we know that indicates a power of 1, times O3 also raised to the first power. So from this rate law, we can tell that NO is first order and O3 is first order. To get the overall reaction order, we add up our exponents. So since both of our reactants are first order, overall the reaction would be second order. Let's look at the second example down here. 2NO plus 2H2 produces N2 plus 2H2O. So again, we have two reactants, NO and H2. And in this rate law, we see NO has an exponent of 2, so NO is second order. And H2 has an exponent of 1, so H2 is first order. Notice that this does not correspond to the coefficients. In the balanced equation, both reactants have a coefficient of 2. However, only NO is second order. H2 is first order. There is no correlation between coefficient and reaction orders. Overall, the reaction order for this reaction would be 3. So we have a second order plus a first order. Alright, so how can we determine reaction orders from our kinetic data? So if you remember previously, when we take kinetic data information, we have our initial concentrations of each of our reactants, and we have rate information. So when we start our reactions, we know the initial concentrations of both reactants, and we can gather our rate information by studying the change in concentration over the change in time. Now, in order to determine reactant orders, we need to vary the concentrations of our reactants to determine what happens to the rate. So in this example, we have NH4 plus NO2 minus produces N2 plus 2H2O. We have information about both reactants, concentrations are varied, and we look at what happens to the rate. So if I want to find reaction orders for each of these reactants, I need to isolate them from the other. So for NH4 plus, I need to see what happens when NH4 plus changes concentration, but I need to hold NO2 minus constant so that it doesn't interfere. So if I look at experiments 1 and 2, NH4 plus concentration is doubling between experiments 1 and 2, but the concentration of NO2 minus stays constant. So I'm removing any effect that NO2 minus would have on my rate. So this means the doubling of NH4 plus is what is giving me my change in my rate information. And between experiments 1 and 2, I see that my rate is also doubling. Alright, so when NH4 plus doubles, my initial rate of the whole reaction doubles. So if you remember previously of our 3 different types of reaction orders, seeing the same effect with concentration and rate is indicative of first order. Now if we look at NO2, we want to see NO2 minus change, but NH4 plus remain constant. So I can look at experiments 5 and 6. I see NO2 minus doubling, NH4 plus staying the same. And then I can look at the rate information. And I see my rate is also doubling. So if my NO2 minus doubling produces a doubling of the rate, again that suggests first order. So I have first order for NH4 plus, first order in NO2 minus. So when I write my rate law, I have rate is equal to our K, which we haven't calculated yet, times our NH4 plus to the first power, times NO2 minus to the first power. Now our rate constant K can also be determined from this experimental data. Once we know our reaction orders, we can then go back and solve for K using any of our rate trial data. The rate constant K is going to be the same for every reaction. Doesn't matter what the concentration changes are, but each reaction has a unique K value. Alright, since both of our reactants are first order, we would say overall our reaction order is second order, and this will determine the units for our rate constant K. Rate constant K has units based on the concentration units, time units, and the overall order of the reaction. So this chart shows you overall order of the reaction being 0, 1, 2, or 3, and what the units of K would be. Now these units assume that rate is in molarity per second, and concentration is molarity. So if our overall order of reaction is 0, remember then our rate is equal to K. Rate has units of molarity per second, so our K would have the same units. If our overall order of reaction is first order, then our rate is proportional to concentration. So the units of K would just be 1 over seconds. If it's second order, we again divide by another molarity, and our units of K are liters per mole seconds, or 1 over molarity times seconds. third order, we divide by molarity again because we have another concentration to worry about. So we have liters squared over mole squared times seconds, or 1 over molarity squared times seconds. The general formula is given below. So we can see the trend. Every time our reaction order goes up by 1, we are dividing by another molarity unit. So our units of K are inverse molarity raised to the total order of the reaction minus 1 over our units for time. Usually the units for rate are molarity per second, but we can calculate rate using minutes or hours or days or even years. When we talk about radioactive decay, normally we're talking about time in terms of years. Alright, let's see if we can calculate what the value of K would be. Since we know the reaction orders for NH4 plus and NO2 minus, we can pick any of our experimental data to fill in for our rate information. So let's just look at experiment number 1. So if we look at experiment number 1, filling in our concentrations and our rate information. So we have our rate is 5.4 times 10 to the minus 7. We're going to divide by our concentration of NH4 plus and divide by our concentration of NO2 minus for experiment 1. When we do that, we get a K value of 0.00027. Since our overall reaction order is second order, this would be 1 over molarity times S. No matter what experiment number we pick, we should get the same value of K. So even if we pick experiment number 8, and we take 43.3 times 10 to the minus 7, and then divide by 0.2, and divide by 0.0808, we get the same value for our K, 0.00027, 1 over molarity times S. Now that we know a rate law, we have our K value, we have our reaction orders, now we don't have to perform the experiment anymore because we can just use this expression to calculate what the rate would be. We can fill in any concentrations now of NH4 plus and NO2 minus and calculate the rate. So let's do this in this example. What is the rate of the reaction when NH4 plus is 0.3 molar and NO2 minus is 0.09 molar? So now that we know that the K value is 0.00027, we can multiply by 0.3 to the first power times 0.09 to the first power, and we find that our rate is 7.3 times 10 to the minus 6 molarity per second. Alright, let's see if we can calculate reaction orders and our K value for this example. NO2 plus CO goes to NO plus CO2. So we have 3 different experiments. We want to find the reaction order for NO2. We need to pick 2 experiments where NO2 is changing so we can see the effect, but CO is constant. So experiments 1 and 2, we see that NO2 is quadrupling, but CO is constant. And then we look at what happens to rate. Now you may not be able to tell right away that this is a 16-fold increase, and that's okay. You can do your ratio of your rates. So in this case, 0.08 divided by 0.005 will show you that it's a 16-fold difference. Same way you knew that 0.4 divided by 0.1 was a 4-fold difference. I recommend putting the larger number on top so that you get a whole number for your difference instead of a decimal. So if quadrupling our concentration caused a 16-fold increase in rate, that indicates second order reaction. It's 4 squared. So NO2 is second order. Now we want to look for the reaction order of CO. We want to pick two reactions where CO is changing, but NO2 is constant. Alright, so we're going to pick 1 and 3. So between 1 and 3, CO is doubling, NO2 is constant, and rate is also constant. So if doubling my concentration had no effect on rate, that would indicate that I have a 0 order reactant. CO2 concentration changes do not affect the rate. So NO2 is second order, but CO is 0 order. Therefore, I would have second order overall for the reaction. Alright, in this last example, we're going to look at pictures to determine rate information. So we have 4 experiments, just like we have in a table, but this time we have pictures. We have 2 reactants. Reactant A is the red, reactant B is the blue. So if we alter the amount of A and B, or red and blue, for each of our experiments, we get different rate information, and the rate is given on this line here. Alright, so the first thing we need to do if we're going to figure out the rate of this 4th experiment is we have to find the reaction orders. We have to know how changing the concentration of A and B affect the rate. Alright, so we're going to employ the same method. So if I want to know the reactant order of A is the red ball, so if I look between experiments 1 and 2, my red is doubling from 2 to 4, my blue is staying constant at 2. So this is a doubling effect for A, and if I look at my rate information, my rate is also doubling. So doubling concentration of A doubles the rate, so A should be first order. Alright, let's do the same thing for B. If I look at experiments 1 and 3, my A is staying the same, but my B is doubling from 2 to 4. And then I can see my rate is quadrupling. So doubling my B quadrupled the rate, indicating that B is second order. So in this example, A is first order and B is second order. Now knowing that, we can determine what the rate for experiment 4 should be. There's a couple ways to do this. The easiest way is to look at experiment 3 and compare it to 4. So if we look at experiment 3, we have 2 red compared to 4 red in experiment 4. So A is doubling. But we have the same amount of B in both experiments. There's 4 in each. So we can ignore B, it's not changing. But A is doubling, and A was first order. So if I double a first order reactant, what should happen to rate? It should also double. So if I'm starting out with a rate of 2 times 10 to the minus 4, my rate of experiment 4 should be twice that, 4 times 10 to the minus 4.